Okay, so I've had some people ask me about beta oxidations and making a video for that, so we'll just jump right into it. I've made up this triglyceride here. It's got three different fatty acids. As you can see, I've labeled them A, B, and C. And first thing you'll need to do is to cleave off your fatty acids from the glycerol backbone by just using a hydrolysis reaction or adding water. And so this is what you're going to end up with for the first fatty acid. And I make up this little template on the right hand side, and I'll explain that. So um, every round of beta oxidation, you're going to cut off two carbons to make one acetyl CoA. So you're going to cut from the left. So I count from the left every two carbons and make a cut. So 1, 2, cut. And that's what that red line is for. And then I'm left with 3 at the end. So we'll just save that for now. And I'm going to explain to you why I've kind of come up with this, or this is what we talked about in our SLA. So each round of beta oxidation, you're going to get 4 ATP, and you can see that here. This is just one round of beta oxidation. In the first step, you make a FADH2, which gives you 1.5 ATP, and in the third step, you get an NADH, and that gives you 2.5. So that's where the 4 comes from. And then this 10 is, you're going to multiply that by the number of acetyl-CoAs that you get from beta oxidation. So here, since I've done one round of beta oxidation, I'm going to get one acetyl-CoA. And I don't get this second acetyl-CoA because I'm left with a 3 carbon at the end. So if I were to make another cut here, I would just have 1 carbon, and you need 2 carbons to make an acetyl-CoA. So I'm just going to have 1 there. And then so I'll fill it out like this. 1 times 4 is 4. 1 times 10 is 10. And you're going to have 2 ATP loss for the activation because you have to add the CoA-S right here using 2 ATP equivalents. And then your 3 carbon at the end, that's going to turn into succinyl-CoA. And so you're going to actually end up getting 4 ATP from that. It takes 1 to activate, and then you can see here, this is how you convert the 3 carbon fatty acid into succinyl-CoA. So this first arrow is representing the 1 ATP that you need to use to activate the enzyme, which is kind of like biotin. You have to activate the HO, this one right here, bicarbonate, that's what I'm looking for. You have to activate that using ATP, and then that way you can add it to make succinyl-CoA, which at the point you feed this into Krebs cycle, it ends up giving you 5 ATP. That's how we net 4. This is a picture of the TCA or the Krebs cycle, and in the yellow here I've circled where succinyl-CoA feeds in, and this is here I'm just explaining to you why you end up getting 5 ATP at the point it's fed in. So you get 1 GTP here, which is an equivalent to 1 ATP, 1 FADH2 here, which is 1.5 ATP, and step 8 here from that dehydrogenase, you get 1 NADH, which is 2.5. So 1, 1.5, 2.5 gives you 5. So for the first fatty acid, we got 16 ATP, so keep that in mind. And the second fatty acid, I do the same setup. Every 2 carbons, I make a cut. 1, 2, cut. 1, 2, cut. And then here I'm left with these 2 at the end. So if I fill in my numbers here, every 2 carbons, I get, or every 2 rounds of beta oxidation, I get 4 ATP. So that's 8 from the actual process of doing beta oxidation. And this time I'm going to get 3 acetyl-CoA because I'm left over with the 2 that are circled in the green there. So the 2 acetyl-CoAs I get from doing beta oxidation, and then the +1 for the extra 2 carbons that's left over at the end, minus my 2 for my activation. And I also have to account for the level of unsaturation here in the second fatty acid because I have a double bond already created between the beta and gamma carbon. So we're going to have to subtract 1.5 ATP because it is between the beta carbon and the gamma carbon. So this is how you can explain that. This is just a sheet I got from SLA. you've already got this bond created between beta and gamma. So using an isomerase, you can move it so that it's in the alpha beta position. And here you can see this is the same picture I had before of just regular beta oxidation. You're coming in now at this step right here. After you've done the isomerase reaction here, you put the double bond between the alpha and beta, and now you look more like this. So you're starting beta oxidation here. Therefore, you don't get the 1.5 ATP you create from the first dehydrogenase reaction and beta oxidation. So that's why you have to end up minusing the 1.5. Okay, so third fatty acid, it's a little bit more complex. So I do the same setup though. Every 2 carbons I make a cut. So 1, 2, cut, 1, 2, cut, 1, 2, cut, 1, 2, cut, and fill in everything here. So I have 4 cuts. So 4 times 4 is 16. And again, I'm left over with 2 carbons at the end rather than 3. So I have to add 1 to my number of cuts to get 5 acetyl-CoAs times the 10 ATP those give each when they go through Krebs cycle. Gives me 50 minus the 2 for the activation. And then I'm going to show you both of these double bonds here. So I'm actually going to only end up minusing 1.5. The reason is if I look at this first one, this is a bond between the gamma and delta carbon, which we actually don't end up subtracting any ATP from that. However, after the second cut right here, my ketone, since this whole left side is going to be gone after 2 rounds of beta oxidation, my ketone is going to get put on this carbon right here, on the delta carbon. Therefore, I now have alpha, beta, gamma. Right here, I've got this second double bond is between a beta and a gamma carbon. So therefore, I'm going to lose the 1.5 ATP from that. So to explain to you the first double bond, the reason why you don't subtract any ATP from the first double bond when it's between gamma and delta is this sheet here from SLA again. You still have to do the first dehydrogenase reaction, so you get that 1.5 ATP from the FADH2, because that's essentially going to do the same thing it normally does in beta oxidation and put a double bond in between your alpha and beta. The difference here is you have to use a reductase to basically reduce the number of bonds that you have. So reductase, you reduce the number of double bonds to 1. So you put it though in between beta and gamma. So you have to use another isomerase to get it back in the right position, and it's back between alpha and beta, and you can go through the rest of beta oxidation. So here again is where you'd be coming in. You're coming in at the yellow again, but you're not. You've already accounted for this 1.5 when you did it right here. So you continue through beta oxidations 2 through 4. Since you don't do step 1 here again, but you've already done step 1 earlier, you have no change in the net ATP when the double bond is between a gamma and a delta carbon. Hopefully that didn't lose you there. So then the last part is the glycerol backbone. And so this is a feeder mechanism that we have to know, or a feeder pathway, I should say. And this is going to end up giving you 18 ATP. And just a brief explanation on that. The conversion from glycerol into dihydroxyacetone phosphate, you're going to use 1 ATP, get out an NADH, and then this DHAP can feed into glycolysis, eventually yielding pyruvate, which then goes through the PDH complex to give you acetyl-CoA, and then through the TCA cycle, and you get your ATP equivalents of NADH and so on. So that's why you end up with 18.5 ATP for that. This is just a quick conversion of the glycerol, how it's converted into dihydroxyacetone phosphate. So you can pause it here if you need to look at this, but you can see where the ATP is put in and the NADH is generated. And then this is going to go into glycolysis. So our total net ATP count for the first fatty acid, we got 16. Second fatty acid 34.5, 62.5 from the third, and then your glycerol is 18.5. So we get a net ATP of 131 for that fatty acid I made up there. So hopefully this might help you out a little bit. If you've got questions, please feel free to let me know, message me on Facebook or whatever, and hopefully we can help you out. So thanks. Good luck, guys. Have a good Thanksgiving.